Okay, so this is chapter 29 notes. Again, we did these live and now they are here on video for you, so you can watch them as many times as you want. Well, chapter 29 is all on particle physics. And it's the idea that light is a wave, but we're now going to treat it as a particle, right? And so whenever we see the word photon, we're thinking of a particle of light energy, that it's given off in these packets that are integer values of h. H is a known constant and given in joule seconds or electron volts per second. Not electron per second, it's electron volt seconds. Remember, a joule and an electron volt are both units of energy. It just depends which one you're in, whether you want to use the electron volt or the joule version of it. But this is on your table of information, nothing you need to memorize. You should understand the concept that the energy of one photon is equal to h times f. So if f goes up, energy goes up. And if lambda goes up, since it's backwards, energy goes down. So that's important to know. So a photon that looks like that is going to have low energy when you compare it to a photon that looks like that, which is going to have high energy. Of course, it's a particle, right? So you can imagine little particles beep, 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 that are moving like a wave is what I always picture them as. So the photoelectric effect is one of those concepts that helps us understand how it can act as a particle. So you have the sheet of metal that is someplace, and then you have this light that comes in, and then it all of a sudden makes the electrons move. So if you have it hooked up to a circuit, maybe it's a light bulb, I don't know, it'll start moving. There's no battery. You just end up with an EMF that we've talked about before, and it pushes your little electrons around. So that's the concept. So that's why it has to be a metal. It has to be a metal because it has to be it has to be conductive, right? If there's no, you can do this on plastic all day long and nothing's going to happen because you can't get those electrons to move. There's a minimum frequency energy to dislodge the electron, right? So you can get an electron to, if there's not enough energy coming in and the electron doesn't go, then you get no electricity. So you need a high enough energy so that electron will start moving. And the amount of energy is known as the work function. That is energy, right? Because it's HF naught. It's the minimum energy. If this coming in is too big of a wavelength, then it's not going to make the electron go. So then there's no electricity. If it's going faster, so let's say this one makes it dislodge, then this one would make it go faster, right? Because there'd be more energy given to each electron. So remember, each photon has this amount of energy and knocks one electron. That's the important thing. It's one electron. So if I have multiple of these coming in, each one knocks its own electron, and each electron starts moving. So you can end up with more current. So you can end up with faster current. You can end up with more current depending on what you do. So this is showing you the equations for photoelectric effect. I'll have to do this demo separately because it doesn't work with explain everything. So I'll do a separate demonstration of this part that you can click on if you would like to watch it. But for now, or you can do it yourself, right? You can go to the photoelectric simulation and you can play with it. But the idea is that, so here's red, and red has a low frequency, right? It has a big wavelength, so it has a low energy, and its energy is not enough for potassium that needs at least 2 electron volts to be able to get an electron to go. So if we shine green, green has a little more energy, 2.25, so we get a little bit of energy, the velocity turned into kinetic energy into velocity. And then if we have purple, even more, it's going to go even faster, right? So 6.22 compared to 2.96. So you'll see the energy of the photon is either HF or HC over lambda. We know those are the same. Notice we have K max for both of them. Work function can be a phi naught or W naught. I don't like it as a phi naught, but you should just know that it is, because to me that should be flux. But it is used, so just be aware that, and I don't know if it's, I want to say it's WF or phi F and not with a naught, but anyways, that's the equation. That's the energy that it takes in order to make it. If we're graphing like you did in your lab, you're going to have the kinetic energy max on one side, and you're going to have the frequency on the other. So remember, when you did it, you measured voltage, right? Delta V, and we know that delta V times Q is equal to energy. And so in this case, it's Q out of an electron and the V that just knocks it out, and that's equal to H times F. So that's where that equation comes from, right? Do you see it? The V is this V, and the QE is this one, and the energy is kinetic energy. Again, in the simulation, if you go watch, I will show you the stopping voltage, but the idea is that you shine the light in and you get electrons moving, but then you can put a battery in here, right, that's going to push it the other way, and when you make the current just get to zero, right, then that's known as stopping voltage, because you're basically pushing it back. And that's a way to be able to figure out what the work function is, right? Because that's the minimum energy that you can get it to go. So when we did in the lab, remember, you just made it glow, the LED, which is a little bit different, but similar concept, right? And then you took your voltage and you changed it into Qs, and you graphed your KE and your frequency. The slope is equal to H, and the y-intercept is equal to negative, right? So across this down here is your negative work function down here. Then we have this thing called the Compton effect. Compton effect isn't about energy, it's about momentum. So it's kind of like the photoelectric effect is more about energy, and momentum is more about momentum. Well, Compton effect is more about momentum, but both of them have to do with the fact that you have mass of things coming in. The Compton effect only happens with X-rays. That's important. So you end up with X-rays. You start with X-rays. You end with X-rays. But now you've got this electron that gets sent out, and then you end up with a different amount of energy. So you notice that the wavelength went up, which meant the energy went down, because some of the energy went to this electron. Or we can even look at it, I guess it's better than saying energy. It should be the momentum would be even better than saying the energy, because like I said, photoelectric is more about energy. So the momentum goes down, and the momentum, this gains momentum, right? So it's basically a bouncy collision. And so that's why you have a higher frequency to a lower frequency, so the momentum is conserved, right, as you transfer it from one. But again, Compton only happens in the X-ray. You have to have that amount of energy to make anything happen. And this is like the target material. I know it just looks like an atom, which it is. It's an atom of something, but it's some target material that will actually make this happen. And they all have a definite characteristic of what you can see depending on what the material is, because it depends on what electrons it sends out, how much energy they have. So the idea, again, momentum conservation, that's why I said not really energy, momentum conservation. So this is the momentum of the lambda coming in. This is the momentum of the should be an electron. I don't know why I have a P there. And then the momentum of the other one, right? So this would be the light coming in. It hits its target. The electron comes out. So that's the electron's energy or momentum. See, I keep saying the wrong thing. And then we have energy that comes out. That's momentum of the energy that comes out, right? So lambda in, lambda out, electron. So when we're looking at this, we can remember from last year, of course, that P is equal to mv. And we skipped this chapter, but E is equal to mc squared. I think you'd believe me on that, because it's a very famous equation. And of course, E is equal to hf. So I could write mv, because it's moving, remember, it has to be moving close to the speed of light. So I could write as mc squared over c, right, because that's mc. And then that would mean that that is equal to hf over c, right? Because it's the energy is mc squared, so that's hf, and then divided by c, see it, right? Because mc squared is that, right? Which is that, and then still divided by c. But f over c is lambda. And so now we can see that light has momentum, and it's going to be equal to h over lambda. So again, as lambda goes up, P goes down, which makes sense, just like energy. It's the same equation we had here, right? It's this one just. And so the Compton equation, we have the lambda of an electron is given as H over MC from that same equation, right? We rearranged lambda and MC, because that's, anyways, it works. And so that's equal to 2.43 times 10 to the negative 12 meters. Not a number you need to memorize. It would be given to you if you needed it, but it's known as the Compton wavelength of an electron. So you can find the wavelength of an electron based on that equation if you just do H over P, right? So the lambda is just going to be equal, and I have that later in the notes, but just so we can understand it. And it's just that P is usually equal to MC because it has to be close to the speed of light. If it's equal to MV and V is really slow, right, then it just doesn't work because H is so small, it just basically breaks down. It's not a useful equation. So if we're looking at the difference in the lambdas, right, between the lambda coming in and the lambda coming out, it's going to be equal to the lambda of the scattered electron, because basically we're just looking at the momentum, right? And so since momentum's H over P and everybody's got H in the party, then we can just say the differences can be equal to the scattered one. But then you have to take into account the fact that it would at some angle, which is theta. And so it's 1 minus cosine theta for the angle it gets scattered at. But the important thing is that the lambda prime is greater than the lambda the lambda that scatters is greater than the lambda that came in because it has to lose energy momentum due to conservation of momentum. So here we'll go back to that concept I was just talking about, that this means that particles can act like waves and waves can act like particles. We did the radiometer demo. Remember that was, and you could do it with hot and cold water, but I didn't. But it has a little thing in there and it's got a black side, and if you shine a light on it, it makes it spin. But it spins due to the difference in heat, not in the fact that there's photons that bounce off of it. But it's the idea that that a wave can act like a particle, can have a wavelength. So the de Broglie, I know I don't say it right, but that's what I like. The de Broglie wavelength is given by that equation, which is H over P, which is basically H over MV, and in some cases is H over MC. So that's where we got the equation for the wavelength of a electron, right? Because you can put an ME, and that becomes for an electron. But you can do it for anything, right? So you could decide what your wavelength is depending on how fast you move, but it wouldn't be very big, right? Because you'd be really, right? Because you don't move very fast. So anyways, you don't act like a wave, hate to tell you. Then we have this thing called the uncertainty principle, that you can't figure out where things are, and so this is showing position and momentum, and you can't know your position and your momentum at the same time. It's also true for energy and time. So you basically interact with it, and so if you interact with the particle, you can't know everything about the particle, and so it just becomes kind of, chicken and the egg kind of problem. So here's it stated. This is all you really need to understand, is that you can't observe a particle without interacting and changing something about the particle. And so you have uncertainty in one of these. You could have it in both, right? But you could know the momentum and then you just have uncertainty in position. Or you could know the energy and then just have uncertainty in time. So it's just saying that, so it could be P delta Y is greater than or equal to H over 4 pi because I know my P and I don't have an uncertainty in my Y, right? So then you would plug in what the momentum is that you know for sure, and you could find the delta Y, and it's H over 4 pi. Same thing with this one. You could know one and not the other one. So this could be E delta T is greater than or equal to H over 4 pi, right? So there's not a lot to that. It's basically a concept. Don't panic on. And then the last concept is just comparing Newtonian to quantum mechanics. So Newtonian's everything we covered up until this time. So it's large particles. V is much smaller than C. The opening is really big, so things are not diffracting. And all of Newton's laws will work for it, right? They apply. That's why we can go out to the solar system and the universe. Everything in it still works, but then we get tinier and tinier and tinier, like you saw in Elegant Universe. And and then things don't work as well. In quantum mechanics, we're dealing with very tiny particles. V has to be very close to C. The opening has to be less than or equal to lambda so it can actually diffract. And then you have Schrodinger's equation. So when you see words like diffraction or interference, right, then you know that you're dealing with quantum kinds of things and you're dealing with waves. And if you're dealing with momentum and you're dealing with energy, you tend to be dealing with your Newtonian physics. So that's it. That's chapter 29.